All right, let's do a little practice with the chain rule. Let's start off with this function. Y is equal to the square root of 5x cubed minus 2x plus 1. Now when you look at this, hopefully you realize that we're looking at a composite function. And there's two functions involved here. I have the 5x cubed minus 2x plus 1. That would be my inside function. And then I have this radical, and that would of course be the outside function. Now whenever we're doing derivatives or integrals and we see a radical, we need to rewrite it. So I'm going to rewrite this as 5x cubed minus 2x plus 1, and that square root gets rewritten as a 1/2 exponent. Again, I have two functions, and if I've got two functions, that means that when I do my derivative, I need to have two separate derivatives. So let's start. dy dx is going to be equal to, I'm going to do the outside derivative first. That outside function is the 1/2 exponent. So that 1/2 is going to come to the front, and then I'm going to reduce the power by 1 to give me negative 1/2. There's my first derivative. The inside function is still the same, 5x cubed minus 2x plus 1. So I've done the derivative of the outside function. Let's move on to the derivative of the inside function, which would be 15x squared minus 2. I have two separate derivatives, and I had two functions to start with. So I have completed the chain rule. Now, if this is a multiple choice question on the AP test, then we probably need to do a little simplification, a little rewriting. So I'm going to do that here. First of all, I've got a 2 in the denominator, so I'm going to go ahead and put that there. I have a negative exponent, which means that this 5x cubed minus 2x plus 1 is also in the denominator. And then that negative exponent is a 1/2, and the 1/2 means that it's the square root. And then the rest of my derivative, the 15x squared minus 2, would be in the numerator. And so there you have the derivative. Let's move on to another example. This time let's do one with a trig function. Just a moment, let me adjust. Here we go. Y is equal to tangent squared of 4x cubed. Now if you look at this function, hopefully you can see that we've got three functions here, three functions together in this composite function. The most outside function, which is of course the derivative we're going to do first, that would be the squared. And if it's hard for you to see that, sometimes it's helpful to rewrite this as tangent of 4x cubed, and then we can put brackets around that and put the squared on the outside. Sometimes that makes a little more sense to people, and if you need to take a moment to rewrite it like that, I think that's great if it's going to help you get the right answer. So now we can easily see that the 2 is our outside function. Then the next function, the next layer would be the tangent. And finally, the most inside function, the last derivative that we're going to do, would be the 4x cubed. So let's start with that outside function. First, dy dx is equal to 2 times whatever, and we're going to reduce the exponent by 1 to give a new exponent of 1. And of course you don't have to write that there. But the inside part here, tangent of 4x cubed, that's still the same. So I've done one derivative. Let's move on to the next function in line, which is the tangent. And of course the derivative of tangent is secant squared of whatever, and that whatever is still 4x cubed. It's very tempting to just put x, but it's still 4x cubed. So that's my second derivative, and now we're going to finish up with the last one, the derivative of the inside function 4x cubed. That derivative, of course, is 12x squared. And so if we go back and look, you can see that we do have three derivatives, one for each part of our composite function. And so we've completed the application of the chain rule. Really not a lot of simplification to do on this one. We could multiply the 2 and the 12x squared to get 24x squared. But then the rest of it is going to remain the same. So your simplified answer would look like that. Let's look at one more example. And this one, I'm going to try to make it a little bit more challenging. E to the 5x squared times 4x plus 1 to the 5th. So I've got a couple different things going on with this one. Notice that we have a product rule, but then each part of my product is a composite function. So for the product rule, I have e to the 5x squared, and then I have 4x plus 1 to the 5th. So e to the 5x squared would be my f, and 4x plus 1 to the 5th would be my g, but each of those is a composite of two functions. So let's see what this derivative would look like. dy dx, if I'm doing product rule, I'm going to start out with f times g prime. So here's f times g prime, and g of course is two functions. I'm going to do that outside derivative first, which is the 5 times whatever to the 4th, and that whatever is still 4x plus 1, times the derivative of the inside function, which is the 4x plus 1. That derivative is 4. So that is my f times g prime. But now I need to do g times f prime. And our f is e to the 5x squared. The outside function there is the e. And of course the derivative of e to anything is e to the anything, in this case e to the 5x squared, times the derivative of 5x squared, which would be 10x. And so that's our complete derivative. Now simplifying this, there's a couple different ways you can go. And it kind of depends on what multiple choice answers look like. But notice we've got a plus sign here in the middle that's separating two terms, and both of those terms have an e to the 5x squared. So it's likely that that's going to get factored out to the front, e to the 5x squared. And then in this first term, I have a 5 and a 4 that I can multiply together, but that's really about all I can do to simplify there. 20 times 4x plus 1 to the 4th. And now I'm at my plus sign. And in the remaining part of our derivative here, let's see, there's not a whole lot of simplification I can do. I can bring that 10x to the front, and then we have 4x plus 1 to the 5th. So that's one possibility of what the simplified answer might look like.